Hello, everyone, and a huge welcome to our St. Paul American School Clark Grade 9 students. I am absolutely thrilled to have you here today for this explainer on G9 Geometry Unit 5, Lesson 11, Similarity and Trigonometry Modeling Project. Today, we are setting out on a truly fascinating mission. We're going to learn how to measure the unreachable. Seriously, have you ever looked up at a towering building or a massive tree and wondered exactly how tall it is, only to realize your tape measure just won't cut it? Well, today we're going to use the raw power of geometry to solve that exact problem. Okay, let's dive into this. Here is our roadmap for today's project explainer so you know exactly what to expect. We'll start with our project objective, then cover the foundation of similarity and trigonometry. After that, we'll do a complete modeling project walkthrough, flag some common modeling misconceptions, pause for a quick formative knowledge check, and finish up with a recap. Section 1. Project Objective. How to measure the unreachable. Moving to Section 2, Similarity and Trigonometry, the foundation of indirect measurement. Before we actually build anything, we really need to understand the underlying theory, right? We can't just trust the numbers blindly. We need to know why they actually work. When we dilate a figure, meaning we shrink or enlarge it from a center of dilation using a specific scale factor, we create an image that is mathematically similar to our original pre-image. And this brings us to a massively important rule, the angle-angle or AA criterion. Through similarity transformations, we establish this AA criterion, which essentially proves that if two angles of one triangle are congruent to two angles of another, those two triangles are similar. This means their corresponding angles are congruent and their corresponding sides are perfectly proportional. This is literally the bedrock of trigonometry. Because of this AA criterion, trigonometric ratios like tangent, sine, or cosine work completely reliably no matter how massive or tiny the triangle is. Section 3. Modeling Project Walkthrough, using a clinometer for indirect measurement. Let's put on our lead engineer hats and shift from abstract theory into our concrete step-by-step Ohio Department of Education modeling project. Now, what's really interesting about this setup is just how beautifully simple it is. This ingeniously simple instrument is called a clinometer. You can actually build one yourself using just a regular drinking straw, a standard protractor, and a string weighed down by a hex net. By looking directly through that straw at your target, the weighted string hangs straight down naturally due to gravity. You can then just read the angle it creates right there on the protractor. In our specific project scenario today, this simple tool is going to help us find an exact angle of elevation of 10 degrees. So let's walk through the exact setup shown here. Imagine you, the student, are sitting in a chair facing a wall. We first measure the horizontal distance from the wall to your eyes, which comes out to exactly 120 inches, or 10 feet. We also measure the vertical height from the floor up to your eye level, which in this model is 36 inches. From this seated position, you look through the clinometer straw at a specific point high up on the wall, determining that your angle of elevation is exactly 10 degrees. Notice how this physical setup perfectly creates an invisible right triangle in the air between your eye, the wall, and the exact point you're looking at. To solve this indirect measurement model, we're going to guide ourselves logically through three very precise steps. Step 1. We explicitly note our horizontal distance to the wall, which acts as the 120-inch base of our triangle. Step 2. We take that angle of elevation we just found, 10 degrees, and set up a tangent ratio because we already know the adjacent side and we really want to find the opposite side. Step 3. Once we calculate the length of that opposite side, we have to remember to add our initial 36-inch eye level back into the final result. That's the only way to get the total true height from the floor. Let's zoom in on step 2 for a second. This is the specific tangent equation derived directly from our setup. Tangent, as we know, is the ratio of the opposite side over the adjacent side. In our right triangle here, the opposite side is the unknown height on the wall above your eye level. Let's call that segment BC. The adjacent side is our known distance to the wall, which is 120 inches. Therefore, the tangent of 10 degrees equals BC divided by 120. By calculating this out, you instantly solve for that missing vertical chunk of the wall. Section 4. Common modeling misconceptions. Pitfalls to avoid in your project. Let's switch into safety check mode for a minute. So the crucial point is avoiding a few very common errors identified in the New Mexico Public Education Guidelines. First, do not mistakenly compare non-corresponding angles. You absolutely must ensure you're comparing the exact corresponding pairs between similar triangles. Second, be extra careful not to incorrectly apply the scale factor when you're dealing with dilations. And finally, failing to list the vertices of similar triangles in the correct order is a major trap.
Listing vertices in order is absolutely essential for correctly identifying those proportional sides we rely on for our trig ratios.
Section 5, Formative Knowledge Check. Let's test your understanding before you attempt your own measurements. Okay, here is a direct question from the source material to really challenge your understanding of the physical model. Think back to our clinometer setup. We spent time measuring the distance from the floor up to the student's eyes, which was 36 inches. Why is that specific measurement absolutely necessary? Like, what would actually happen if we just skipped it? Take a brief moment and formulate your answer. Well, if you said it was because of the starting height, you are exactly right. The triangle calculation, our tangent equation, only finds the distance from the student's eye level up to the target point on the wall. It completely ignores all that empty space between the floor and the eyes. Therefore, that 36-inch eye-level measurement absolutely must be added back to our trigonometric solution to find the total true height from the floor to the target. Forgetting this final step is hands down the most common reason a perfectly good math equation results in the totally wrong real-world answer.
Section 6, Recap. Summary of required concepts. Let's wrap this up.
And this brilliantly illustrates exactly how abstract math connects directly to the physical world around us. To summarize our core takeaways, similarity transformations establish the AA criterion, ensuring our angles and proportional sides remain perfectly consistent. Because of this, we can totally trust trig ratios to solve for unknown distances in those similar right triangles. We use incredibly practical tools like clinometers to capture our angle of elevation. And crucially, we must always remember to add the initial eye level height back to our final trig calculation to get the true height. So the final provocative thought I will leave you all with today is this. Now that you have the literal power to measure the unreachable using just a straw, a string, and some right triangles, what seemingly impossible structure are you going to measure first? Thank you so much for joining me for this Explainer Grade 9. Happy measuring!